The newest images of 3I Atlas just came in, and they're telling us something important. On November 11th, astronomers Jewitt and Luu pointed their telescope at this interstellar visitor and published their findings with a straightforward title: 3I Atlas still single. That means it's still one solid object, not broken apart. If you want to stay updated on this topic, make sure to subscribe and leave a comment, and now let's get into it. They didn't just glance at it and call it a day. They examined a region around the comet spanning 500,000 kilometers. That's an enormous search area designed to catch any fragments if they existed. They used multiple analysis techniques to hunt for signs of breakup: brightness stretching to amplify faint objects, contour mapping to trace structural details, false color imaging to highlight different materials, radial ring analysis to scan outward from the center. Every method was specifically chosen to detect even small pieces. What they found was a single bright nucleus at the center. That's the solid core. Around it, they observed a complex coma, the glowing cloud of gas and dust, with active jets shooting out in multiple directions. They documented two tails pointing in opposite directions. One tail extends away from the sun at about 301 degrees, which is the expected direction. The other tail, called an anti-tail, points almost directly toward the sun. They measured it at 106 degrees while the sun was positioned at 115 degrees. That's only a 9-degree offset. Anti-tails are uncommon, but have been observed on other comets before. The critical finding is that despite extensive searching with multiple techniques across a vast region, they found no evidence of fragmentation. While tracking this object, researchers have documented some unexpected changes in its behavior. There have been brightening events that weren't predicted by the models astronomers were using. The comet has gotten brighter at times when calculations suggested it should either dim or remain stable. These brightening episodes are currently being studied to determine what's causing them and whether they're connected to changes in outgassing rates or surface activity. Additionally, this marks the third recorded instance of the comet displaying a blue-green color. These color changes aren't random visual effects. They likely indicate shifts in the type of molecules being released from the surface. When comets release different chemical compounds, the way they interact with sunlight changes the color we observe. Blue-green hues are often associated with specific molecules breaking down under solar radiation. Each time 3I Atlas changes color, it suggests the composition of the outgassing material or the rate at which it's being released is shifting. Researchers are working to connect these observations to specific chemical processes happening on the surface, but what's clear is that the object remains dynamically active as it continues its path through the inner solar system. Recently, the Meerkat radio telescope array detected radio signals coming from 3I Atlas. When radio emissions are detected from comets, it typically draws attention from the research community because it's not the most routine type of observation. Some researchers initially noted the detection and discussed what might be producing the signals. The explanation that emerged is consistent with natural cometary processes. The signals are attributed to hydroxyl, represented chemically as OH. This occurs when water molecules on the comet are broken apart by solar radiation. When H2O molecules split under the sun's energy, they form hydroxyl radicals, and these radicals emit radio waves at specific, well-known frequencies. Meerkat was detecting exactly that emission. While the initial detection generated some discussion, the consensus interpretation among researchers points to standard cometary chemistry. The signals fall within the parameters expected for an active comet that's releasing water vapor as it's heated by the sun. The detection adds to the dataset on 3I Atlas, and even though it's an interstellar object, the radio emissions appear consistent with processes observed in solar system comets. There's an important observational window approaching. On December 19th, 3I Atlas will reach its closest point to Earth, passing at a distance of approximately 270 million kilometers. While that's still a significant distance, it's close enough for ground-based and space-based telescopes to collect high-resolution data. Observatories around the world are coordinating observation campaigns to maximize the scientific return during this period. There's also a possibility that NASA's Europa Clipper spacecraft could pass through portions of the comet's ion tail. If this intersection occurs, the spacecraft's onboard instruments might directly sample particles and gases being released by the comet. This would provide valuable in-situ measurements that complement remote observations. Direct sampling offers information that can't always be obtained from telescopic observations alone. The JUICE spacecraft is also conducting observations of the comet as part of its science operations. Between coordinated ground-based telescope networks, space telescopes, and potential spacecraft encounters with the tail material, the coming weeks should yield substantial amounts of new data. These observations are expected to help researchers better understand the comet's composition, internal structure, and the mechanisms driving its observed activity patterns. To put the November 11th observations in proper context, it's important to understand what 3I Atlas recently experienced. On October 29th, the comet passed through perihelion, its closest approach to the Sun. At that distance, it was subjected to intense thermal stress. Solar heating causes ice on the comet to rapidly sublimate, transforming directly from solid to gas. This sublimation process generates internal pressure as gas escapes from beneath the surface. For some comets, particularly those with structural weaknesses or fractures, the pressure generated during perihelion can be sufficient to cause the nucleus to crack or fragment. This is why researchers were paying close attention to how 3I Atlas would respond to perihelion passage. Some early discussions among astronomers suggested that the thermal stress might lead to structural changes or fragmentation. The images captured 2 weeks after perihelion show the nucleus remains intact as a single object. It continues to actively produce substantial jets of gas and dust. This indicates there's still significant volatile material at or near the surface that's sublimating. The fact that it survived perihelion passage without fragmenting provides researchers with information about its structural integrity and composition. Whether it's more cohesive than some predictions suggested, or whether the gas release is occurring in a way that distributes pressure more evenly, the observations give scientists a concrete data point for understanding how interstellar objects respond to solar heating. Looking back at early November on the 9th, images captured by telescopes showed 3I Atlas had developed extensive tail structures. One tail stretched millions of kilometers in the standard direction, pointing away from the Sun as solar wind and radiation pressure push material outward. The anti-tail extended millions of kilometers in the opposite direction, toward the Sun. These are large-scale structures containing significant amounts of gas and dust. What made this notable was the timing. Images taken just a few days prior to November 9th showed minimal or no visible tail activity. The rapid appearance of these extensive structures raised questions about the timeline and the physical processes behind such dramatic changes. Gas released from comets typically travels at velocities around 1,500 kilometers per hour. While that sounds fast, it's relatively slow in astronomical terms. To build up tails that extend millions of kilometers at that velocity, standard models would suggest continuous outgassing over an extended period, potentially weeks or months of sustained activity. The quick development of these prominent tails indicated something different might be occurring. Either the comet experienced a sudden, significant increase in activity, perhaps triggered by a specific event or threshold being crossed, or the way the released material was spreading and becoming visible didn't follow the typical gradual timeline. The sheer scale of the tails, combined with their rapid appearance, suggested the comet was releasing material at rates considerably higher than what would be expected from steady-state sublimation alone. This prompted discussions among researchers about what mechanisms could drive such rapid tail formation. Standard cometary models generally assume relatively steady outgassing rates that build tails progressively over time as the comet approaches the Sun. If 3I Atlas departed from that pattern, it could indicate either episodic outbursts of activity, structural changes in the nucleus exposing fresh volatile material, or perhaps compositional differences that affect how quickly material can be released and dispersed into space. Understanding why would add to our knowledge of cometary behavior, particularly for objects originating outside our solar system that may have experienced very different formation conditions and evolutionary histories. When researchers began analyzing the comet's activity, they performed calculations based on the observed brightness and extent of the coma and tails. These calculations suggested the comet would need approximately 1,600 square kilometers of actively sublimating surface area to produce the observed output of gas and dust. If you were to model that as a spherical object, it would correspond to a nucleus roughly 23 kilometers in diameter. That's the size needed to support the activity levels using standard sublimation rate calculations. However, measurements from the Hubble Space Telescope indicated the nucleus is approximately 5.6 kilometers across. That's significantly smaller than the calculated requirement. One interpretation of this discrepancy is that the observed activity level appears higher than what the measured surface area would typically support. It's similar to observing more heat output than the size of the heating element would normally produce. Early estimates of mass loss suggested the comet was releasing around 50 billion tons of material per month. The challenge with this figure is that the comet's total estimated mass is approximately 33 billion tons. From a straightforward accounting perspective, this appears problematic. An object can't lose more mass than it contains unless there's fragmentation or the calculations need adjustment. There's historical context for seemingly impossible mass loss figures. In 1992, comet Shoemaker-Levy 9 fragmented, and the total material it released exceeded initial mass estimates for the original comet. Once researchers confirmed it had broken into 21 separate pieces, the numbers made sense. Fragmentation creates more total surface area exposed to solar heating, allowing increased sublimation rates. Multiple fragments mean multiple sources of gas release. Some researchers initially proposed that 3I Atlas might be undergoing similar fragmentation. If the nucleus had split into multiple pieces, that would explain both the high apparent activity levels and the extensive tails. More fragments would mean more combined surface area absorbing sunlight and releasing volatiles. However, the November 11th observations by Jewitt and Luu showed this isn't occurring. The comet remains a single intact object. This leaves researchers considering alternative explanations. One possibility is that the mass loss calculations overestimate the actual material being ejected. If the tails are particularly efficient at scattering sunlight, they might appear brighter and more extensive than their actual mass would suggest. Brightness doesn't always directly correlate to mass in a simple one-to-one relationship. If factors like particle size distribution or dust-to-gas ratio are different than assumed, the apparent brightness could be misleading. If the actual mass loss is closer to 5 billion tons per month rather than 50 billion, the discrepancy becomes much more manageable. That's still a high rate, but it falls within plausible bounds for a nucleus of this size. Another hypothesis, though more speculative, involves the comet's extreme age. 3I Atlas is thought to be very old, possibly between 7 and 10 billion years. That would mean it spent billions of years traveling through interstellar space, continuously exposed to cosmic rays. Cosmic rays are high-energy particles that can alter the chemical composition of materials they strike over long timescales. One speculative explanation is that this extended bombardment modified the surface chemistry. The James Webb Space Telescope observed that 3I Atlas has approximately 8 times more carbon dioxide relative to water compared to typical comets from our solar system. One proposed mechanism for this unusual ratio is that cosmic rays gradually converted carbon monoxide present on the surface into carbon dioxide over billions of years. This interpretation remains speculative and would require additional verification. The hypothesis extends further. If cosmic rays created an altered crusty layer on the surface through chemical modification, that layer might cause ice beneath it to sublimate in non-standard ways. The altered crust could potentially create channels, pockets, or pathways that effectively increase the surface area from which gas can escape, even if that area isn't directly visible from outside. This would be a way to reconcile the high activity with the small measured size. However, this remains a theoretical proposal. There's no direct observational evidence yet confirming this specific mechanism is at work. The fundamental challenge is that the calculation methods used to estimate mass loss and required surface area have proven reliable over decades of studying solar system comets. These methods have been validated across many different comets with varying activity levels. If these standard approaches aren't accurately describing 3I Atlas, researchers need to determine why. Is it because the object originates from outside our solar system and formed under different conditions? Is it related to its extreme age? Is there something about its internal structure or composition that hasn't been identified yet? These are the core questions driving current research efforts. The current observational data shows an intact nucleus, which differs from some early interpretations that suggested fragmentation might occur. Multiple hypotheses are being considered to explain the activity levels and behavior observed. Researchers continue analyzing data collected from various instruments, both ground-based and space-based, working to build a comprehensive understanding of this object. The December 19th close approach will be an important opportunity. Additional observations during that window will add to the dataset, and more data helps refine theoretical models. If the activity continues at similar levels, if the color changes persist, if brightening episodes occur again, each observation adds constraints that help researchers evaluate which explanations best fit the evidence. What's evident is that 3I Atlas provides scientists with a valuable opportunity to study an interstellar object during an active phase. Whether the explanation ultimately involves cosmic ray surface modification, recalibrated mass loss estimation methods, unusual sublimation mechanisms, or some combination of factors. Working through these questions advances our understanding of objects from beyond our solar system. The scientific process involves forming hypotheses based on observations, making predictions, and then testing those predictions with new observations. That process is ongoing here. We'll learn more in the coming weeks as new data arrives. If you found this breakdown helpful, make sure to subscribe and drop a comment sharing what you think about 3i Atlas and the different explanations researchers are exploring. Thanks for watching, and I'll see you in the next video.